Hello everyone, welcome to lecture number 16. Today's topic is asynchronous processing. So we're going to introduce basically a new building block in building architectures. I think this is probably the last big new building block that we'll be talking about. Last time we talked about strategies you can use to choose between the many different kinds of databases that are available, and we went through different categories I've sort of chosen for describing the databases that you'll find out there, as well as the examples of them. I kind of broke them into three big categories here. I guess we're using the term data store to include also distributed file systems in this comparison, because I think that you can kind of think of them as interchangeable with NoSQL databases for some applications. And the main point of that lecture was to show that your choice of database will depend mainly on the structure of your data. In other words, because all these databases provide different data abstractions for organizing the data, as well as the pattern of access. You know, how scalable does it need to be, whether and the balance between reads and writes and stuff like that. We also talked a little bit about transactions and why those are difficult to implement on NoSQL databases, although available on some of them. Transactions are easiest on SQL relational databases. So although those tend to be less scalable, it gives you that's one of those features that you get most easily there. So that's something you can kind of trade off the ease of transactions with the scale in some sense. All right, so today we're going to be talking about asynchronicity and coupling. By coupling, I just mean like the connection between two things, in particular in your architecture. And I'm going to start by talking about responses. So I'm going to show diagrams in this lecture that show time passing downward, and arrows represent a request being sent, and these arrows are kind of are slanted because it takes some time for a message to arrive. So the client sends a request, it travels to the server, it takes some time to arrive at the server calculates some response, that takes some time, it sends the response, and it takes some time to for that message to arrive from over the network. Okay, the purpose of the response from the client's perspective is can vary depending on what the request was. I mean, sometimes the whole purpose of the request is to get some data back, in which case the response is like the whole reason why you made the request. Sometimes the response is very short and just acknowledges that the request was received and that the request was acceptable. Or conversely, if you make a bad request and there's a failure to process it, you might see in the response some error code. So for all those reasons, responses are important, and the client needs to read a response from the request generally, especially when we're talking about synchronous APIs. So far, everything we've talked about has been a synchronous API, like REST APIs, where you make a request, you wait for the server to handle it, the server gives you a response, and then you move on. And the response code you get, whether it's 200 OK or something else, gives the client information about whether the request succeeded. So it's synchronous in the sense that the client waits for the server, and when the client gets a response, it knows the server's done. We also call those blocking requests. Now there's an alternative, which is asynchronous or non-blocking, and we're going to be talking about that today, motivating why you would want to use that kind of request and understanding the trade-off between synchronous requests and asynchronous requests. Okay. Now, to motivate it, we're going to think about a request that's really long. So for example, this could be a request that involving a lot of other services. So in this case, I'm trying to deliver an email. So if the client sends a message to its mail server to deliver an email, that mail server has to then turn around and deliver that email to a relay. That relay might have to deliver it to another relay, and eventually it gets delivered to the receiver's mail server. If that mail server is going to give an acknowledgement, it has to go through the same chain potentially to get back to the client. So delivering an email, when you send an email, if you want to actually know at that time when you're making that request that it was delivered, the time between that request and response could be very long. And if you're using that API in an application, waiting for a long time before you get a response is a bad thing, because you want to be able, because you want the UI to continue. You don't want the user, like the human user, to get stuck on that operation waiting for that message delivery verification to get back. Most probably you just want to know that the first hop received the message and then continue on, right? So the asynchronous alternative does just that. So you send the request to your mail server. The mail server acknowledges that it received the request, and that maybe it does some simple check of the formatting of the email to make sure that it's valid. It checks, that you have the right password, that you're authenticated, that it trusts you to be a valid mail user. So it tells you the message is acceptable. It tells you that it will try to deliver it, but at this point, it doesn't actually know that it will be able to deliver the message. This is an asynchronous interaction, right? Because we told the server to send or deliver an email, and it told us not that the message was delivered, but simply that it received the request and it will try now to do the operation, right? So then after that, the mail server does all the things that are necessary to make it happen, right? So the advantage here is that the client gets a response quickly. The client gets some feedback. It's important that the client gets at least some feedback because networks are unreliable, servers can go down. So we don't want the client to have no response at all, because then it would not even know whether the internet was working, whether the mail server was accepting the message. If we just acknowledge that simple thing and not the full delivery, we can do it very quickly. Okay, so the client can move on to doing its other thing. To free up the UI, if you have a box for sending a message, you click send. The server gives an acknowledgement. That means that window can now close, and you can move on to doing the next thing. Or if you're doing it through the web, you move on to the next page. Now, the downside of this, of course, is the client didn't really learn whether the request was successful. It only really learned that the first step was successful. In other words, that the mail server, the sender's mail server, received it. There's a bit of a trade-off there. When we moved from a synchronous request to an asynchronous request, there are a few things that changed. We actually were the same. Ideally, the same work is going to happen. Like the message is still going to be delivered. We actually still can use a REST API to do this, to implement an asynchronous API. But the difference is in the meaning of the requests and of the responses. So notice that originally the request was asking the server to deliver an email. And I'm highlighting the word deliver because that's going to change. The response is an acknowledgement of delivery. In other words, that the message was actually delivered to the endpoint. With the asynchronous style, the request became a request to send an email, not necessarily to deliver it. Sending an email is just the first step in the process of delivering a message. And the response we get back is that the server acknowledges that it has attempted to send the email, or you could reword this to say that the message is on its way, in transit, something like that. Okay, so you give a response still, but the response is less meaningful or less powerful than it was in the first case, but you get the response quicker. Now, that's all well and good. So the benefit is the client can move on. What you may have noticed is that the client loses the ability to get complete feedback about what happened, right? So we have a fire and forget request, which is to say you start it and then you move on. But that's not always good enough. Sometimes the client wants to have an asynchronous request, but still be able to see what the final results are of the operation. We want to be able to proceed immediately, but later we want to know whether the request succeeded, and we might want to get some response data, or if it failed, we wanted to get an error code or something like that. But we don't want to wait for it initially. We want to kind of have our cake and eat it too. Can you think of a way to support this? To have an asynchronous API that nevertheless is able to provide feedback to the user about the eventual result of the request. What do you think? Pause and think about that, please. Well, I have a couple options. The first one is to use a database to store that result. So we create a request record immediately. So when the front end server, the first server that you reach, or the server that handles the request, gets the request, it's going to give a response pretty quickly, but not quite as quickly. It's going to do a little bit of work. The little bit of work it's going to do is to create a request record in the database that has a unique ID. So it's going to create a placeholder in the database that will eventually store the result, and it will tell the client what the ID is of that placeholder, of that result, in other words. So the server updates when the server eventually finishes the full chain of work, the whole job, the whole request. It will update that database record. Update that database record to have all the details of the completed result. So, and later on, what the client can do is it can check to see what the results were. Okay, so the client has to do another request, a second request, to check the status later on. So I'm showing three requests that might be involved in that asynchronous interaction with the request record. So I'm showing here first the request and then the response. So the first one is that you post a message attempt. This is just the API I'm inventing for this. The response you get back is an email ID. Okay, so this doesn't tell you whether it succeeded or failed, but this is the request record. So it's saying that, okay, I'm accepting this message generation request and I'm giving you an ID that you can use later. Okay, so later on, the client can send another request to check the status of that message using the same ID that was passed back. The service will check the database. If it checks too soon, it might get a status of pending, like the resource record, request record might still be empty, so to speak. But eventually, after the request finishes, then when the client makes another request, it will get detailed information, like, for example, that the request failed and what specific error message might have been given. Okay. Now notice, of course, the client has to remember to make this request. It doesn't know exactly when to make it, but it just can keep trying periodically, perhaps. So that's kind of a simple approach that just requires you to have an extra table in your database to store these request records. Right. Another option, which I'm calling option number 2, is to call back to the client. So the client sends a request, the server acknowledges, and then later on the server actually kind of pushes to the client. It's kind of like a push notification in a sense. But the way that I'm specifying this, or the client specifying this, is with a webhook. And this is done in practice for backend services that have interactions. So what the client does is it specifies, essentially specifies the REST API endpoint that should be called by the server when it's done. And this works if the client is actually a server. So it's like if this is a server-to-server communication where the client is actually always running and it's not natted, it has either a public IP address or an IP address that's on the same, that's reachable from the server in any case. It can provide a webhook. So what I mean by that, a webhook or a callback, you can kind of see in this example. So the client sends a request post message attempt, just like before. They also are including additional information. I'm including it here in a request body. So I'm saying the callback is this URL. Okay, so this IP address at the beginning, 3.3.3.3 in this example, is the IP address of the client that's making the request, probably. And so it's saying, okay, you can contact me when you're done. Here is how you can contact me, by making a web request to this URL. And I will listen for it and get your response that way, right? So then the backend sends a request, in this case, which is a post, to the message complete URL path, which was specified in the callback. Okay, and they both would have to agree on like what the format of the message is that should be sent back through the callback. But that's one way to do this. It's not, yeah. I was gonna say it's not super popular, I would say, because of the requirement that the client actually is operating a web server to listen, but it is doable in some cases. Another option number 3, is a simple one, which is to have some kind of side channel for feedback. This is less powerful, I guess, but somehow easier. So in this case, the client makes a request. I'm just showing it at a high level. Like, let's say you use an e-commerce site to purchase a book. The server says okay, or the website gives you an acknowledgement saying that your order has been placed. But in fact, to fulfill the book purchase, there's a lot of stuff that has to happen on the back in the back end to make it work. Like, a person might need to check a shelf to see whether the book is actually still in stock, or they might have a database that says that the quantity of that book available is more than 0. And so they think they can fulfill your order, but then actually when a person goes to the warehouse to try to fulfill your order, they find that actually there was an error in that information. A book was dropped on the floor and lost or damaged. So they actually don't have that book to ship to you. So in that case, what might happen is, again, the backend gives you the asynchronous response, gives you a response that the work will be done asynchronously. And then when the failure eventually happens, we use a side channel to give that error feedback, that there was in this example, it's saying charge failed, like if your credit card is denied later on. Or the other example I started with was if the item was out of stock, that also could be a message that you could deliver over email. So you have the client sending a fire and forget request. If you expect failure is not very common, if this is some kind of system where you have an email address for the user, you could send an email back to the customer that gives like a description of what the error was. Okay. Another way that works for services that people are using. Of course, you can also send a text message if you have their phone number. If you're talking about more automated services, you might also just log the error. So you write down the error message somewhere in your system so that one of your staff can look at it later, or maybe whether it's someone on your technical staff, like in DevOps, or someone on your customer support staff maybe would review that error, and they might then figure out, use their best judgment for how to deal with the error. Okay. Now, based on what I said so far, the examples I gave, can you think of some requests in a scalable system, some kind of web-based maybe system, some kind of big software system, scalable software system, that would benefit from asynchronicity? In other words, where you want to have requests that are processed in the background, let's say, or like where you give a response back to the client before the request is fully completed. What do you think? Pause and think about that. I think one good guideline to keep in mind is that these should be things that take a long time to complete, right? So what kinds of things take a long time to complete in a software system that a client might request? So here's some examples I came up with. So maybe transferring a file, something that involves transferring a file over a network, or fetching a file from tape storage or some other storage system that involves mechanical moving of media. Something you might run into while working on the projects for this class is creating a virtual machine on the cloud. That takes a while. Like when you use the UI to create a new virtual machine on Amazon, it gives you it reacts to your action by saying, okay, like done, but it still has a spinner. It shows a spinner and then it works for a while before it's actually finished. So that creation of the virtual machine happens asynchronously. Purchasing a shopping cart, I already showed that example. Booking a flight or a concert or sports ticket, that's something that you often might buy online, but this website kind of warns you that you're going to get a confirmation later when it's finally finished, because they need to check another system. It takes a while for them to actually verify that the seat is still available, for example, in the flight or in the concert. Another example, a LinkedIn connection request. You request a connection to someone else, and that person needs to actually, it's not a technical, it takes a long time, not for technical reasons, but because a human needs to respond to your request before it's finished. So whether or not your LinkedIn connection request was accepted or denied requires a person to respond to it, right? So you can think of that as an asynchronous request. Sending a push notification, another example. Sending a text message, that can take a long time because there could be retries involved when people are out of radio contact, and it involves interacting with a third-party service, typically like Twilio, to do that. We'll see later on in the next lecture that posting a tweet is something that might, if you have a lot of followers, it might take a long time to do that action on the back end. If the implementation has sort of materializes each user's feed separately. And finally, I have two examples of analytics things where we have user events or user actions that some kind of big tech company wants to record for their behavioral modeling, but it's not critical. This is just information they're gathering to use later. Right? For example, when you're using Google and you're clicking on a search results, in addition to navigating to the result, there's also a Java request JavaScript request that runs in the background to tell Google which link you clicked, so that they can refine their recommendation system, basically, so they can determine which search results are actually the best for each term, and also so they can update their behavioral model about what kinds of things you personally are interested in. Same thing for Amazon. If an Amazon user searches for dog toothbrush, of course, there are two things that need to happen there. The first one, the obvious thing, is that you need to navigate to a page that shows results for dog toothbrushes. But the second thing, which is lower priority, Amazon wants to collect the information that you, in particular, were searching for dog toothbrush, and therefore that tells them something about what kind of products and services you might be interested in the future. So that update to your behavioral model is something that can happen asynchronously. Like Amazon doesn't need to update their machine learning model for how to recommend things to you immediately. They can defer that work until an appropriate time, and they might wait until they have several different searches from you before they bother to update your model. Okay. So the way that we provide asynchronicity the way that we implement asynchronicity in our own systems is through queues, message queues. So I'm showing an example here where we have an action that we want to happen asynchronously, which is the posting of a tweet. In next lecture, I'll talk in more detail about a Twitter example, kind of like a simplified version of Twitter and a historical progression of how their system has designed at a high level. But if you're creating a tweet, if we assume that's an operation that actually is expensive, like for example, if you have a lot of followers, then we don't want this service to do all the work to handle that posting a tweet before it gives a response. We want to do it asynchronously. So we give it a 200 OK immediately. As soon as we take that work, bundle it up into some kind of a message, and put it on a queue. So we have this work queue, which stores tweet publication work that should eventually happen, and we have a publication service that pulls off of that work queue. So we post our tweet, the app kind of proceeds to the next screen after we get a 200 OK. In between, but all this backend does is it gets my request, it probably checks some authentication, and it takes the information I provided, in other words the tweet, and puts it in a queue to be handled later. Okay. Doing that is fast because it's just a kind of a data copy of like I'm taking the data you gave me, maybe reformatting it a little bit into a slightly different format, but not really doing much work, just some string manipulation to create a message I can put in this queue. Okay, so the benefit of this, like I said, is that it allows this post to proceed quickly, even though there's a lot of work that might need to happen for that tweet to really be published. We can decouple the slowness downstream from the user upstream. Okay. It also allows us to smooth out the work that this publication service has to do. So if we think of this as one machine, maybe, we can keep it busier if we have a queue that allows work to like pile up when this system is busy, so that when it becomes idle, if we have traffic goes up and down, we can kind of smooth it out and work at 100% capacity if there's a queue to store the messages when the system is at its busiest. So we can handle short bursts of traffic beyond the system capacity by just queuing up that work, as long as eventually the request rate declines. Okay, so message queues store requests that are ready to be handled. So that's this work queue here as an example. Putting a message on the queue is kind of similar to making an API request, like a REST API request. The content of the message defines the request. So if you are like implementing this publication service, instead of having an API for this publication service, like a REST API, what you're going to do is define the message format for messages to be put on this queue such that the publication service will know how to interpret them. Okay, and then if someone wants to use the publication service, they don't send like a REST request to the publication service. They just know what format of message is required by this publication service. They structure the request into that message, and they put it in the appropriate queue. Okay, so the formatting for the messages is a contract, just like the in-apps API is. Like, it defines what is a valid request. In other words, a valid message is a valid request. Okay. There's some terminology here that you should be aware of, because queues in general use a lot of different terms for the same pair of things. So my preferred term, I guess, is producer and consumer for a queue. So the producer adds stuff to the queue, the consumer pulls stuff from the queue. The thing the producer does is either called a push, publish, or produce. Like, the producer pushes, publishes, or produces messages. That all kind of means the same thing. The consumer pulls, pops, consumes, or subscribes to messages. Subscribe is like maybe the most unusual term for it that you would not have heard of just from like a data structures class. But that's a common term for queues in big software systems that are like that you connect to over a network. And so in particular, the combination of publish and subscribe is often used together. You can call a queue a publish subscribe system. You have producers publishing, and you have consumers listening, and you can sometimes have more than one producer and more than one consumer as well hooked up to the queue. Although this example shows one schematically. Another term here is topic. So optionally, you can take a message queue and kind of partition it into several virtual queues by having different topics. So topics correspond to different types of messages, basically. And as a consumer, you might only be consuming one. You might only be subscribed to one topic, which is to say you're only consuming one type of message. So a normal queue, just has an operation to pull from the head, or pop from the head, or tail, or whatever the end of it, whatever you want to call it. DQ, I guess, and queue and DQ, I guess, are two other terms. Those are obvious because they have the word queue in them. Right, but if you have if you have multiple topics, what that allows is the consumer to only get messages for that one type if it wants to. Okay. So it allows you to use one physical machine or set of machines to implement multiple queues by having different topics on that. Okay. All right. So to use this queue, to show how this queue is used, I'm going to show an example with Twitter publishing tweets, and it's going to involve two different queues. So, and I want to go through here a sequence of how a request is handled. So the mobile app here makes a REST API request to post a tweet that goes to this backend server, which I'm calling the API kind of vaguely. So the API receives the request. It has to do a little bit of work in this case. It might check the authentication microservice to see whether the session ID in this request is valid and to see what user it corresponds to. So it makes a request to this other microservice to do a check of that session key, and that checks its database and decides the user is valid, and it returns the user ID back to the service. Okay, so now this backend service knows that it's probably going to give a 200 OK response. It's not going to give a 403 forbidden response. The next thing it does is it creates a message that kind of encapsulates all the relevant information from this request about the tweet, like the text of the tweet, who it's from, what time it was created, all that stuff. Puts it in a message and puts that in this queue. It puts a tweet creation job or tweet creation message, two ways of thinking about it, on this queue, and those will be processed later. So that's the asynchronous part of it. It doesn't wait for the message to go through the queue; it just adds it to the queue. Once that's done, this API server will send the 200 OK response back to the app. Okay, so when the app gets its 200 OK, it knows a few things. Like, it knows that it had permission. It was recognized as being a user who's allowed to tweet, basically. But that's about it. So I want to ask you, is this success response premature? Are there things that can go wrong? Maybe, but it's unlikely. And it'll be a while before we know, and that's why we decided to decouple it. So to look further down into the pipeline, this work queue, this queue of Twitter, of tweet publication jobs, or tweets that are queued up to be published, Those are handled by a publication service in this design. The publication service just continually in a loop pulls off tweets from this queue. It sees the type of the message is a published tweet job, so it processes it. So it has to do some work to do that. That might involve checking a followers database or followers table to see who should get that tweet. It might go through a loop to update all the followers with that tweet to build out the feeds for all those users. It might also see, and that might be like millions of followers. We'll talk more about this Twitter example in the next lecture and why I've designed it in this way. Actually, you might think it's weird to do all this work when there's maybe a simpler way to do it, but I'll talk about why we're doing it this way in the next lecture. Okay, so I'm updating maybe millions of feeds. That's going to take a long time, right? A lot of database updates. There might also be @mentions in my tweet which indicate that certain people should be notified, and also certain of my followers might have alerts enabled for my tweets, so they want to actually get both of those groups of people might want to get a push notification in response to this tweet. Right? I mean, not all my followers are going to get push notifications, but some of them might. So when the publication service is going through all those followers, it is making a record of who should get a notification, and it is creating notification jobs in this notification queue. That's another thing that's going to take a while potentially to complete, and there are also going to be potentially a lot of those for each one of the tweet creation jobs that was observed. So I create some number of notification messages here. Those are going to have a different format than the tweet messages. That's just going to have the information necessary for the notification server to do its work. Basically, like what's the user, what's the message that they should get in the notification, and that's about it. Right? The notification server at the other end of this different queue, right? It's again constantly reading off it's pulling messages off this queue to handle them. The kinds of messages it's handling are different because it's a different queue. The messages it's getting are notification messages. And when it gets one, it will check its push notification database to see like what the proper way of notifying the user is. Maybe it sends them an email. Maybe it is to connect to the smartphone push notification server or whatever to do that. So it's going to do whatever work there is for each of those messages to complete it. All right. Now, what happens if there's a failure here? Like if, for example, we try to send an email to the user and the email bounces back, I guess it would take a while for that to happen, but maybe more simply, let's say we try to send a push notification and the push notification server tells us that user ID is no longer valid. Well, we might retry a few times here, but we don't really have notice that we don't really have a way to notify the original generator of the tweet that 2 steps downstream and maybe 10 seconds later some notification failed to be delivered. But it's not really a big deal because the original tweeter in this particular case for this application, the original tweeter doesn't really care that a notification for one of their followers didn't work. Okay, so this decoupling in 2 stages actually is fine for this application. It doesn't really present many problems, and there's no real need to do any of the workarounds I mentioned, like the response records or callback functions, because this mobile app that made the request doesn't really care. I mean, the mobile user would care if somehow the publication service failed, but we don't expect that to happen. We expect that if the authentication passed, that the tweet creation message that goes into this queue should somehow be publishable. All right. So we saw some trade-offs here between tightly coupled systems, which are synchronous systems on the one hand. That's what we've been talking about so far in this class up until now. Those are simpler to design and build because there's no ambiguity about whether things succeed or fail. There's instant feedback when things fail, and we don't need to have queues at all. With loosely coupled asynchronous services, some of our operations can be faster because we're doing work in the background, but it makes it harder to give feedback. So when there's a failure, it's harder to respond. So that's okay if those failures are not important and they can be ignored, or we have to have some way to make a record of those errors and somehow check them later. That was the response record idea. on the other hand, even if the client knows later that there was an error, like if I send an email and then, 2 days later, my app tells me like your email from 2 days ago failed to send. If it doesn't also have the content of the message and like who it was sent to, that's not a very useful error. Although, there might be a way to, of course, implement the system so that you did keep a copy of the message until it was confirmed, but that makes it more complicated. I also mentioned that you can use side channels like email to alert users if there's some kind of failure later on. You always have, generally you have these side channels to handle like really bad errors if they do happen. Okay. One of the benefits of decoupling, besides making responses faster and allowing progress, is that they also help scaling. They make the job of scaling easier. Mainly because, or for several reasons, we can decouple. We can scale producers and consumers separately. So it might be that the producers, at any given time, you can have like 5 producers and 3 consumers in this example. That might be the right balance to handle your load because the consumers are doing less work. So you have that flexibility to do that if these things are separate. We also can smooth demand by deferring work. So you might need fewer consumers overall if the work they're doing can be delayed. In other words, it can be queued up here. And we also can think of these message queues in 2 ways, actually. So it's funny. They're similar to 2 other building blocks we've talked about. First of all, I think of them as similar to databases. They're kind of a specialized kind of database. Message queues are like a database for storing work requests that are optimized for writing to the end and reading from the beginning, or pushing to the back, pulling from the front. If that's probably better terminology. We also can think of them like load balancers because we can have lots of consumers reading from the same message queue, and that's kind of like having one load balancer in front of multiple clones of a service, right? It's a way of distributing. It's a single place to put work where that work can be distributed across a lot of different workers by having those workers pull from the same queue. Okay. All right. Now, I'm going to talk now about some, implementation variations and different kinds of queues. So far, the discussion of queues has been very theoretical. But there are a few different, when you go to actually implement a system and use a queue, you have to choose between different types of queues, and I'm going to give some guidelines for that and talk about what's available. So the first distinction I want to make is between 2 categories, passive queues and active queues. This is a pretty simple concept. A passive queue is like probably what you would think of by default. This is a queue that accepts messages. This is like the database version. It's just the thing that stores stuff, that accepts where the consumers, where producers push to the queue and the consumers pull. So the consumer has to periodically request messages, or whenever the consumer is ready to work, it sends a request to the queue to pull off a message from the front of the queue, right? That's a passive queue. We call it passive because the queue itself is not starting work. It's just listening and accepting requests. It's reacting to the outside, right? It's reacting to the producers pushing data to it, and it's reacting to the consumers asking for data, asking for messages. An active queue is a little different because it actually will push out messages to consumers. So in this case, you have to actually configure the queue to know where to send the messages, and the queue will actually push messages out to the subscribers. The subscribers have to listen. So it's a little bit of a different design. Okay, by default, I would think mainly about passive queues because those are simpler to reason about. And there's some queue softwares that handle both modes of operation, but I guess active is a little bit more advanced. You also have to think about what happens when the subscriber is not listening or fails to accept the message or is too busy to accept messages, and maybe you have some kind of failover rule, or you go through a list or something like that. But that's kind of complicated, right? But those are 2 different types of queues, and both are used in practice. There also are different ways of thinking about queues, and you can implement queues at different architectural levels and achieve the same theoretical decoupling. So basically, I'm going here at the top from like the smallest queues to the biggest queues. We can have small queues, which are just like things in memory. Like if you're in your programming language, you have access typically to data structures that you can use to implement queues in memory. Those in-memory queues can implement the same principle I've been talking about so far of decoupling producers and consumers, and but it's happening all in one machine. So maybe like that queue is a queue that's in memory can help to distribute work between threads that are running in the same computer. For example, the executor service in Java is a work queue that distributes work to a thread pool, where the thread pool is the set of consumers. That's typically not what we're talking about when we're designing architecture. An architecture diagram for a big software system. We typically would not go into the detail of describing like what's happening within a software application to the point where we would specify that there's an in-app queue. But keep in mind that can be there. You have that option when writing your software to use a queue inside. There also are just a little bit bigger than that would be a separate queuing application. So on your virtual machine that's running, let's say if you're using Java, your Java service, you might also have another application running on the same computer, on the same machine. For example, Suro, which is an open source project from Netflix that actually I worked a little bit on a few years ago. That's just like, it's a software that is designed for queuing. It stores stuff in memory, but it also stores it to disk as well. So if the machine is powered off or something and you restart it, you'll have the messages saved there. And you can use that to, if you have requests going into your machine, and either and you want to be able to accept them, give responses quickly without necessarily the work being finished, you can implement that kind of a queue in front of it. So if you want to just decouple your service from at the machine level, you decouple requests from the application that's running on that machine, you can use one of these queuing applications. But really what we're talking about in this class most importantly is this third class, which are distributed message queues. And these are clusters. These are like dedicated machines, kind of like databases, that implement a queue for a big system. And they actually are implemented in a distributed way, typically with more than one machine that works together to implement a robust, scalable queue, where if one of the nodes fails, that's okay. The system doesn't stop working. Well, depending on how it's implemented, you might lose some messages in the process. So it's kind of like a NoSQL database in a sense. It's a distributed data store, but the data it's storing are messages in a queue. Okay, and this allows all your work in a system to go to one big queue in the middle and be distributed later on. So examples of this are Kafka is probably the best example, the most well-known example. Also, ActiveMQ, RabbitMQ. Amazon has a managed queue called SQS, and these are like huge. Like Kafka can handle a ton of requests. So to compare those three, or like to understand what the difference is, I'm listing some pros and cons here. So an in-app queue is simple. There's no separate app to deploy. The downsides here are usually like you're just using an in-memory data structure, so it's not stored to disk. So if your app crashes or reboots, you would drop those messages that were in memory. A separate queuing app does typically have disk backing, like it has a file that stores your messages. So if the machine reboots or an app crashes, you don't lose messages. But if the whole disk fails, of course you lose the messages. So it's limited to one machine, and the robustness is limited to the robustness of that one machine. But it's more scalable than an in-memory application and more robust than an in-memory application. You also can configure this to work in kind of like an active way. This is an example of something that might be an active queue where you don't need to even change your application. You just configure the queuing app to push the messages that come in to the service that's running on the same machine. Distributed message queue gives you like massive scalability, gives you replication, no single point of failure, And because it's so scalable, it ends up being like a big global load balancer in a sense for intermediate work. It can be a single point of coordination between lots of producers and consumers, also because they can handle many different topics. So you can have one big cluster that implements a lot of different virtual queues, which are topics, and it's a single kind of like clearinghouse for all of the work that's going through your system, for that work that like is kind of background processed. One of the downsides is the complexity of deploying this kind of a system, and also consistency side effects. So just like any other distributed database, things can get weird if one of your nodes fails or if you have network problems. So for example, on RabbitMQ, you have to choose between making your delivery guarantee be that the message is delivered at least once or at most once, but you can't get exactly once. So of course, if it's at least once, what that means is that your message could be delivered in duplicate, and depending on how what your software is doing, that could be a problem. That could lead to like things happening more than once you don't want to. At most once is not good because it means that you could, in a bad situation, you could have the message dropped. So that's the consistency trade-off that RabbitMQ gets. As I said, Kafka is one of the most well-known distributed message queues, I guess the most well-known distributed message queue. And I'm showing here a schematic of both how you can look at Kafka. Kafka's in the middle. There's a bunch of producers, a bunch of consumers. There are different topics. The different topics are like sub-queues. And the different partitions represent different machines that are storing the data. So the consumers are pulling from multiple partitions, and producers are pushing the replicas of the data to multiple partitions. So it's kind of like it partitions the data similar to a distributed hash table, with a distributed hash table, or similar to a NoSQL database. One of the things that's different about Kafka than a pure queue is that it keeps messages around after they're read. So it has it stores the messages, and then there's a read offset that kind of like shows where you're currently reading, and different consumers can have different. The reason for this is it allows the same message to be read twice by two different processes that might be lacking each other. So for example, in this example, I have like orders might be listed in this queue, and first there might be actually, I'm not sure which one of these. First there might be a push notification server that processes the message to generate an alert, and then later on there's another service that lags behind that might do start the actual processing of the order. Okay. So the messages are kept around after reading. That is called, so in some sense it's called a distributed commit log rather than a queue, because the term log indicates that the stuff's kept around rather than being discarded after it's read. Just as a little side note, it uses an open source software called Zookeeper for distributed consensus, which is a general distributed consensus system that allows the consumers to agree on the point in the log to start reading. Okay, but although that could have been implemented by Kafka itself, but they kind of like outsourced it to this Zookeeper system, which is a general distributed system for like consensus, which is to say getting a bunch of different machines to agree on something, which is an important fundamental problem in distributed systems. Okay, so when queues fill up, we have potentially a problem, right? You might not. Ideally, it wouldn't be possible for your queue to fill up, but of course, machines run out of disk space or memory, and so you should think about that. And especially if you have, if your consumers are doing a lot of work, it might be that they can't keep up with the producers, right? So what happens when your queue fills up? Well, that's a bad thing, I guess. It indicates there's a problem, and there's no perfect solution to this. But there are different ways to approach this. So you'd want the queue to be able to give an error response to the producer that's trying to add more to it if it's full, and then maybe the producer passes that error response back to the client, so the client sees the system is down. I can't make another tweet now because Twitter's queues for handling tweet creation work are too full. You wouldn't want that to happen, but maybe that's better than just having the user send the tweet and have it just get ignored because there's nothing that the system can do with it because the queue is full. Okay, so it'll stall the service probably back to the user. We call that back pressure. So if queue is full, or like you can think of it like physically as like a tube of water, like it can't proceed through a pipe, that creates back pressure. So if you try to push back on it and try to add more to it, like physically, it prevents that and provides backward pressure. You'd want your DevOps or operations staff to monitor the size of queues to anticipate these problems and make adjustments before they happen. So one of the things that they can do is like scale up the number of consumers to more quickly pull data off of the queue. That's basically the best response, either to do that or to make the queues bigger. Yeah. So another issue that comes up when using queues is maybe ordering, because when you're using a big distributed queue like Kafka, you can't necessarily guarantee strict first in, first out ordering of messages. So if you have several things that are several like pieces of work that you're creating, and if you send it to a distributed queue, you can't be sure that the order you created the messages will be the order that they're consumed in. The simplest way to get around that is just to, if you are generating those messages together, to bundle them together and send them as one big message. But then, it has to be handled in one place, so there's a little bit of a trade-off there. Okay. All right, so just keep in mind that these message queues are backend like systems, backend creatures, as I say here, just like databases. So databases are useful, but you wouldn't have your smartphone app or your web app interact, like make a request directly to a website, to a database, because you have to authenticate those requests. You don't want to have to build your database in such a way that it is like protected from random. It's able to handle all the various kinds of attacks that can happen from the public internet. So message queues generally are not going to be exposed to the public. They're going to be just connected between different backend services, different microservices. So when you're designing your architectures, don't have your front end connect directly to your message queue, to a message queue, and similarly, don't have it connect directly to a database. Okay, so to review today, we talked about message queues. The purpose of message queues was to provide loose coupling between services. So far, we've been talking about tight coupling. So this creates an asynchronous interaction where you ask the system to do something, and it tells you that it will do it later, but it doesn't actually tell you. It doesn't wait until the work is done before giving you a response. Okay, so when you do that, your results are less apparent, and you have to have ways to deal with it. The first way of dealing, I call it fire and forget, and that is you don't deal with it. Like you just have no knowledge of what happened to your request. The other approaches where you actually, to allow the client to actually learn what the response was, or either request records where you give back to the client some ID that they can check in the database to find the result, or a callback where the server you tell the server what web request to make to give the response back to the client. So your APIs in your system can be asynchronous if they are defined as message formats for message queues. So if you want a service to be asynchronous, put a message queue in front of it and define the format of messages that should be put on that queue, rather than just defining the a REST API for the service. Also, I guess another thing I mean by this bullet point is that a REST API can be phrased in such a way that the response isn't a full response, but it indicates that that the work has started and that more work will happen later. Okay. Queues are used to decouple systems. I talked about that. And one interesting way to look at a queue is as a sort of load balancer for deferred work, because lots of consumers can pull from the same load balancer. It also allows you to scale your producers and consumers separately. And finally, I talked about 3 different levels of load balancers, like small, medium, and big, basically. The most interesting ones are the really big ones, the distributed message queues, but you also can have queues in memory or kind of running on disk as a separate app alongside your service. Okay, hope that was useful. See you later. Like I said, next time we're going to apply this idea to an architecture design for Twitter. Okay, that should make it a little bit more concrete. All right, see you later.